Assalamu alaikum warahmatullahi wabarakatuh. So now we will discuss some very important op-amp circuits. Op-amp circuits. Okay. So first of all, we will discuss about an important circuit which is known as comparator. Okay, comparator. So comparator is used to compare. It's used to compare two voltages, basically a basic comparator, two voltages. So it is we have two different types of comparator, and one type is nothing but a zero level detector, and the second one is a non-zero level detector. Okay, so first of all we will be discussing about the zero level detector. So we will be first discussing about zero level detector. Okay, first one. So zero level detector is a simple circuit. It's very simple. We will be using the open loop configuration basically in all this kind of detectors, comparators, and you know that this is minus and this is plus. Okay, zero level means we will put our reference, this is our reference voltage, we will put it as 0 volt. Okay, that means our reference voltage, we will be putting the reference voltage at the negative terminal. You can put it at the positive terminal also, there is no issue, and usually we will be putting it at the negative terminal, and we will put our V reference as 0 volt. Okay, that's why it is a zero level detector, and we will apply our input V in here, and this is your input, and you can see that and this is your output, and your input can be anything like a sinusoidal wave or a triangular wave, anything. Okay, it can be anything. Let us consider this is the V in. Now the op amp, I told you this is in open loop. Basically this is in open loop, so whenever the op amp is in open loop, it may either go to maximum plus VCC or minus VCC. So here I will be representing my maximum voltage as plus Vmax, and the minimum voltage that I am giving here as minus Vmax. Okay, Vmax, sorry. Okay, Vmax. So in open loop, I told you whenever you are giving a small differential voltage here, basically the output will be going into maximum. So you will be, because AOL is very high, and V out is equal to VD times AOL. And what is your VD here? VD is equal to the voltage at the positive terminal, this is V plus, and the voltage at the negative terminal is V minus. So V plus minus V minus. And what is V plus here? V plus is V in, because this is same thing, V in, minus what is your V minus? V minus is your 0 volt. Okay, so your VD is equal to V in, right? Yes. Now I will again redraw this circuit, minus plus, and this is V in, and this is your V reference, which is equal to 0 volt, and what is your V out? V out is equal to VD into AOL, okay, which is equal to V in into AOL. Okay, V in into AOL. Now you have applied your V in at which terminal? You have applied your V in at the non-inverting terminal. So you are giving the input like this. This is your V in. So I can say that what is my VD? VD is equal to V in minus 0. And what is this 0? Is my reference voltage, V reference. Okay. Now if V in is greater than 0, that means if it is, this is your reference point 0, this is your reference point, actually 0 volt. Okay, and this is the time. So if V in is greater than 0, which implies that your VD will be greater than 0, And what will be your V out? V out will be V in into AOL. Since V in is positive and AOL is the gain, voltage gain, and you know that this is having a positive gain because you have applied your input at the positive terminal. So the output will be going into V max, because it will go to V max. It will not be any other value, it will be V max, because the op amp will be one of the transistor in the op amp will be moving into saturation and another one into cutoff. So this is minus V max, so the output will be V max, right? That means suppose V max is equal to 10 volt and this is minus 10 volt, then I can say that the output will be 10 volt. That's it, whatever be the input, okay, the output will be 10 volt. So this is the first situation. Now the second case, if your input, if your V in is less than 0, which implies that my VD, what is my VD? My VD was having this formula, V in minus 0. So VD is equal to V in, and which is less than 0. That means that my output will be equal to V in into AOL, which implies that this is less than 0, V in is less than 0, which implies it is negative value, negative. So my output also will be negative. My output will be minus V max. That means my output will be minus V max. So my output will go to minus V max. My output will go to minus V max. So I can draw like this. If V in is greater than 0, my output will be plus V max. This is my first condition. If my V in is less than 0, my output will be, this is my output, okay, will be minus V max. So I can draw the input and output in the same figure. Suppose this is the input, okay. Now this is V in, okay, and this can be, let's say this is 5 volt, let's say this is 5 volt and this is minus 5 volt and this is, okay, minus 5. Now let's say if V max plus V max is equal to plus 10 and minus V max is equal to minus 10, if this is the case, I can draw my output here. You see, okay, my output here, like when the input is positive, this is the positive, this is negative, this is positive. When the input is positive, my output will be plus V max. Okay, for example, this is equal to 10 volt. Okay, and when the input is negative, my output will be negative. You see this part actually showing it is the transition. So it is minus 10 volt. Anyway, this is minus 10 volt. So up to this point it will be same. After that it will be plus 10 and minus 10, like this. If you consider plus V max and minus V max as plus 10 and minus, sorry, plus 15 and minus 15, the output will be according to that. Okay. So suppose you have another circuit, another example. You have an example. Let's say this is plus and this is V in, and this is a triangular wave which is 2 volt and minus 2 volt, and this is V reference, which is equal to 0 volt. Okay. So when the input become just greater than 0, because your V reference is 0, if the input become greater than 0, your output, suppose this is plus 15 volt and this is minus 15 volt. So I can draw my input and output in the same figure. This is my, okay, that's it. So this is plus 2 and this is minus 2, plus 2 and minus 2, okay, like this. Now I can draw my reference point here, because my reference point is 0, because 0 volt is my reference. That's why I am drawing from this point. Now my output will be plus 15 because these are all positive. So this will be plus 15, and this I can use another color. This is negative, so output will be going to negative. Then again the output will be moving to positive because this is positive, and the output will be moving to negative. That means, so what will be the magnitude of this positive and negative? You see, this is plus 15 and this is minus 15 because this is minus 15 here. So this is plus 15 and minus 15 because the output, the op amp will be moving into the maximum voltage. That's it. Okay, the output will be, so this is the output and this is the input. So this kind of detector which showing a positive maximum, okay, you can say that this is logic 1 positive voltage and this is logic 0, and again this is logic 1 and this is logic 0. In digital circuits, you know what is logic 0 and 1. So 0 means some voltage and 1 means another voltage. So one voltage level and another voltage level. So logic 1 I am assuming it is positive and logic 0 I am assuming negative. So your comparator is acting like a switch. So whenever the input voltage is greater than 0, your comparator will give you a maximum voltage and logic 1, or I can say it's plus 15 in this case. If you are applying plus 5, you will get plus 5. And if your comparator, if your voltage is less than 0, your comparator will give you something less than 0, which is minus 15 here in this problem. So this kind of comparator, this is known as the zero level detector. Okay, so zero level detector is a comparator, but you are detecting the zero level. Okay, you are detecting the zero level. Next comparator, it is non-zero level detector. Non-zero level detector. Okay, so that's what we are going to discuss now. It's non-zero level detector. Non-zero level detector. And what it is non-zero level detector? So non-zero level detector will detect the non-zero levels. That's it. Detect non-zero levels. So here actually it is detecting the non-zero levels. So what do you mean by this non-zero levels? That means your V reference will not be equal to 0. V reference will not be equal to 0. In zero level detector, your reference voltage was 0. So the simple circuit I can draw like this. You will give the input at the non-inverting terminal, always positive terminal, that means V in, and here you will give some reference voltage V reference by using some battery, for example. So this is your V reference, you can say. So this is your V out, and you will be having plus V max and minus V max. Okay, so what will happen here? You see here, this is in open loop. Again, this is in open loop. So the op amp may saturate easily. That means if you are giving a small differential voltage Vd, the op amp will saturate. So I can say that my op amp will give you, what is my Vd? Vd is nothing but V plus minus V minus. Okay, V plus is the voltage at the positive terminal and V minus is the voltage at the negative terminal. So V plus minus V minus. What is my V plus? My V plus is nothing but your V in minus, and what is my V minus? It is nothing but my V reference. So this is my Vd. So I will be getting a positive output if Vd is greater than 0. My output V out will be positive V max. If Vd is less than 0, my V out will be minus V max. So this is my output basically. So that means that if Vd greater than 0 means that Vd is, what is Vd? We have the equation for Vd. Vd is equal to V in minus V reference. So Vd greater than 0 means Vin is greater than V reference. Then the output will be plus Vmax. Then Vd less than 0 means that when Vin is less than V reference, my output will be minus Vmax. Okay, so that's it. So this is the output of the non-zero level detector. So we will see a circuit, then it will be very clear to you. Let us assume that minus, and this is your Vin, and the Vin is a sinusoidal voltage with 2 and minus 2. Okay, this is your Vin, and your V reference, you are applying a V reference here. This is your V reference, which is 1 volt. Okay, and this is V out. So I will draw my V in and V out. First of all, this is my V in, this is my V in, this is 2 volt minus 2 volt, then this is 2 volt, like this. Okay, now I will draw my V reference with another color. This is V reference, V reference. So I will draw my rear V reference will be somewhere here, right? This is my V reference. Now I can draw my output. Okay, my output can be, you see, these are all the portion where input is greater than the V reference. So this portion actually showing V in is greater than V reference. Okay, so I can draw the intersecting points from here, these points. I can draw from these points, I can draw from these points, and between these two regions, you know that the output, the input is greater than V reference. If the input is greater than V reference, the output will be plus Vmax. So the output will be plus Vmax, plus Vmax. And if I take any point below this, then the output will be minus Vmax, minus Vmax. This is minus Vmax. And again, the output is decreasing because all these points are below Vmax. So all these points, V in is less than V reference. So the output will be minus Vmax. And here the V in, if V in is greater than V reference, the output will be plus Vmax. Okay. So like this, again, this is minus Vmax and this is plus Vmax. Okay, like this. Now this is the idea. Okay, now you can have another kind also. Okay, so I hope this is clear to you, this kind of circuit is clear to you. Now we will see another circuit also for non-zero level detector, non-zero level detector. We will see another example. So you have a circuit minus plus. Okay, you are giving a triangular wave as the input, and your V reference is minus and plus. Okay, this is your V reference, which is V reference, which is equal to this is 1 volt. Okay, now this is your V out, and you know that what is Vd here. So Vd, to find Vd, you know this is V plus and this is V minus. So Vd is equal to V plus minus V minus. And what is the voltage at V plus? V plus is equal to V in, basically V in minus. And what is V minus? For V minus, you see this is negative and this is positive. So V minus is minus 1. So this is minus 1. So this is V in plus 1. So this is your difference voltage here. Okay, difference voltage here. So in this case, okay, if Vd is greater than 0, if Vd is greater than 0, if I told you the output will be, if Vd is greater than 0, the output will be plus Vmax. And Vd will be greater than 0 means what? V in plus 1 is greater than 0, which implies that V in is greater than minus 1. That's it. This is the meaning of Vd greater than 0. And another one, if Vd less than 0 means that, what is the meaning of this? If Vd is less than 0, the output will be minus Vmax, that I told you. That means Vin plus 1 is less than 0, which implies Vin is less than minus 1. So if Vin is less than minus 1, you will get minus Vmax. So we will see the circuit. So you see here, I have drawn this as plus 2. I think it's plus 2 and minus 2. Yeah, it's plus 2 and minus 2. So minus 2, and I will draw the line. You see here, this V reference is minus 1. Basically, V reference is equal to minus 1 because you have connected here negative and then positive. That's why. Now you see here, so we will draw here V reference minus 1, and this is 0 volt. Okay. Now you see here, this is intersecting here these 2 points, and I can draw the line. Now for these points, your V in is less than V reference, which implies V out is equal to, I told you V out will be equal to, if V in is less than V reference, the V out will be equal to plus minus Vmax. Okay, minus Vmax. And here these points, throughout these points, okay, and these points here, actually V in is greater than V reference. So that means the output will be plus Vmax. If V in is big one, then output will be positive. If V in is less, then output will be negative. So I can say that my output will be up to this point, my output will be Va positive. This is plus Vmax, and here my output will go to negative minus Vmax, then again plus Vmax. So this is my V out, okay, and this is my V in. Okay, that is the output of that particular circuit. Okay, now you have to draw like this for the exam. So whatever I have told now, I am using a battery here, right? This is a battery. So I have 3 types basically. I can, instead of battery, I can use a voltage divider, because if you want to set the reference voltage as 1.9, then it's not possible by using a battery. Sometimes it will not be available. So we have 3 types basically. What are that? The first one that you have seen, this is your V in, and by using the battery, okay, this is your V reference. So what is this? This is the first type. This is the by using battery reference. Okay, next this is V out. Okay, next is you have another type you will be using. So this is the A, circuit A, and this is the circuit B. Actually you will be using minus, plus, V in. Okay, now you will be using a plus V volt and use some resistance R1 and R2, and by using a voltage division you will be applying here, and this is your V reference. So what is your V reference here? V reference is equal to V divided by R1 plus R2 multiplied with R2. So by changing R1 and R2, you can fix any reference that you want. So this is your V reference. Okay, and the third one, we will see the third one also. You can use a Zener diode also, minus, plus, V in, and I can use, this is a resistance R and a Zener diode. So across the Zener diode, the voltage will be Vz. So this is plus V. So V reference is this voltage. So the V reference will be equal to Vz. That's it. So according to So if you are using a Zener diode, that will be very good anyway. If you want some 5 volt as the real reference, you can buy 5 volt Zener diode and put it there like that. Okay, why you are using a resistance R here? Because to limit the current through the Zener diode, otherwise the Zener diode will damage. So you have 3 types. So the first one I told you, it is having the battery reference. Then the second type is voltage divider reference. Okay, and the third one is the Zener diode as reference voltage. Zener diode sets the reference voltage. Okay, so we have 3 types now. Okay, so the working of all these circuits are same, only you are setting the reference voltage by using different means. Okay, by using different methods. So we will see a problem now. The input signal in figure below, okay, is applied to the comparator in input signal in figure A is applied to the comparator in figure B. Okay, assume maximum output levels of the comparator are plus or minus 14 volt. Draw the output signals. So figure A, I will first write figure, first I will draw figure A, and it is nothing but 5 volt and minus 5 volt. And this is figure B. I am going to draw the figure B. It's a comparator minus plus, and you have some V in here. Okay, and you are applying a plus 15 volt, and from this it is connected here. Okay, and there are 2 resistance R1 and R2, and it is given R1 is equal to 8.2 kilo ohms and R2 is equal to 1 kilo ohm, and this is the V out. So you have to draw the output signal. You have to draw the output signal. So what is V reference now here? I am going to write the answer. V reference, first we will find V reference. What is V reference? Plus 15 volt is applied here. So divided by R1 plus R2 into R2. So plus 15 volt divided by R1 is 8.2 kilo plus 1 kilo ohm, okay, multiplied with 1 kilo ohm. So you will get this as 1.63 volt. So this is your V reference. Now you got your V reference as 1.63 volt, right? So now I can draw my input first. Okay, so my input was 5 volt and minus 5 volt. Okay, 5 volt. Now my reference voltage is 1.6. So I will use, so this is 1.63 volt as my reference voltage. Okay, now you know that the input is applied to the positive terminal. So if V in is greater than V reference, the output will be, V out will be equal to plus V max, which is equal to, it is given in the question that the maximum outputs are plus and minus 14. So plus 14 it will be. If V in is less than V reference, then V out will be equal to minus V max, which is equal to minus 14 volt. Now we will see which portion is above and which portion is below. You see that all these portion are above V reference. That means V in is greater than V reference, and all these portions here, everything, and here also, all these are V in greater than V reference. Again, this portion is showing V in greater than V reference. So I will draw my output with the same axis here itself. I will extend here. So I will first pass my signals here. This is my signal zeros, but you see I will use this and this one to denote the transition points, and this also, okay, this is also, and this one also, sorry, okay. Now you know that for this portion this is above, so it will be, the output will be plus V max. Plus V max means 14 volt, so it will be 14 volt here, 14 volt, okay. And here also, if you take this portion, the second portion, then this also is above, so plus V max, which is equal to minus 14. So not minus 14, plus 14, okay, plus 14. Now the remaining portion, I can say the remaining portion here, here actually I can say that my output is minus V max, which is nothing but minus 14 volt, and here also it is going like this, okay, and here also it is going like this. So minus V max or minus 14 volt. So you are getting plus 14 and minus 14. Now I can join all these lines, join these lines properly. This is my output, okay, this is my output. So I hope this is clear to you, right? Now I hope this is clear to you. Suppose if you want to limit your output not to Vmax and minus Vmax, suppose if you want to limit your output to some other levels, then what you can do? What you can do? So let us consider another circuits with comparator with output bounding. Comparator with output bounding. Comparator with output bounding. I can use a Zener diode for this, okay. So we have first three types of circuit for this. So let us consider, okay, let us consider the operational, let us consider the comparator circuit with output is bounded. Now this is minus, this is plus, okay. This I am going to detect by using my reference voltage. My reference voltage I am setting here 0. You can set any other voltage also, there is no issue, okay. Now let us see one circuit. This is I and this is your V in, okay, and you are using a Zener diode for here. Let's consider a feedback. So you know that whenever we use a feedback, usually the output will be limited. We can limit the output only by using feedback. So I am using a feedback here. Now suppose that if the input is like this is positive and negative. So if the input is positive, what will happen here? If the input is positive, then basically there will be a current. I told you this is 0 volt and this also will be 0 volt if the Zener diode is on, okay. If the input is greater than 0.7, basically if the input is greater than 0.7, otherwise the Zener diode will not be on. So if the input is greater than 0.7, basically what will happen, there will be a current like this. This current also will be flowing like this, and the current will be flowing like this. Okay, and what about this current? There won't be any current into the op amp basically. Now if it is flowing like this, the Zener diode, here it is plus and this is minus and this is 0.7, and I told you this voltage will be same as this voltage when the feedback loop is connected. Whenever the feedback loop is connected, and if there is a current flow through the feedback loop, okay, then due to the virtual short, you see here this is due to the virtual ground. I have explained this concept before. So due to the virtual ground, this will be 0 volt. So what is my output? My output will be equal to, you see this polarity is minus, so this is minus, and the voltage across the Zener diode is 0.7, and this point is 0, that means it is ground. This is ground point. Okay, this is also ground point. So with respect to ground, you see here, you can see something like this. This point, this is your Zener diode, and this point is ground, and this is minus, this is plus, and this is 0.7, and this is your V out. So it will be nothing but minus 0.7. So the output will be minus 0.7 volt. Now if the input is negative, what will happen? That is another story actually. If the input is negative, then the current, if the input is negative, then the output will be positive. Am I correct? Why? Because the negative input is applied to the negative terminal. So negative of negative become positive. So the output is positive. So the current will be flowing back like this. Okay, because current will be always starting from positive and going into the negative. So the current will be flowing back. So if the current flows back, and if the Zener diode is on, Zener diode will be on only if your current is so high. So what will happen? This is plus and this is minus. Again you have the ground point because this is 0 volt. So you will be having a ground point. So I can write my circuit now like this. This is again ground point, even in the positive half cycle. In the negative half cycle. So in the negative half cycle, you are having the current in this direction. This is the current will be in this direction, and this is your V out. So this is positive and this is negative because the current is flowing like this. So if the current is flowing from, this is N-type semiconductor and this is P-type semiconductor. You know that if you take a Zener diode, this is N-type and this is P-type, right? So for the N-type semiconductor, you are applying a positive voltage and this is negative voltage. That means the Zener diode is in reverse bias now. It is in reverse bias in this case. And the previous case, it was forward bias. In forward bias, Zener diode will give you only minus, the voltage across will be 0.7. But here it is Vz. So the voltage across the Zener diode is now plus minus Vz. And you know that this positive is connected here to the positive part. So the output will be Vz. So I will just draw the output, and that will be equal to Vz. So this output will be equal to plus Vz. So that's what happening but if you are using a Zener diode. Okay. Now if instead of this 0 volt, if you are using something different, I cannot actually configure this in a non-inverting configuration. You see here, this is an inverting configuration. If I configure it in a non-inverting configuration, I have to give my input at the positive, and my feedback also will be at the positive. But here I can basically my feedback is negative feedback. That's why I'm configuring like this. But I will give you a question anyway. Before that, I will explain one more circuit. You see here minus, plus, and this Zener diode is connected in an opposite direction. That's it. There is no other change. This is your V out and this is your V in. Okay. Now my V in is like this, positive and negative. So this is my V in. What is my V out? And I told you that we have considered in the positive half cycle, this is 0 volt. If the Zener diode is on, then we will get a feedback path and it will be 0 volt. Now if V in is positive, then the current will be starting like this and it will be going like this, and now this is going like this, and this is N type and this is P type. The current is flowing from N to P. That means that it is reverse biased. If the current is flowing from P to N, it is forward biased, and if the current is flowing from N to P, then it is reverse biased. And the Zener diode will be on with positive here and negative here, and the voltage will be Vz. And your output, you know, this is again ground point, so I can draw along the Zener diode along here now, and the voltage across this is plus minus Vz, and this end I told you this is grounded, this is virtual ground because of that, and this is grounded, and my output, this is my output is directly connected to the minus, so my output will be minus Vz. So minus Vz will be my output. Okay, this is minus Vz. Now I will talk about the negative signal. When the input is negative, I told you the current will be always going into the negative. When the input is negative, since you are applying here to the input is applied to the negative terminal, so the output will be positive. So the current will be flowing like this, okay, like this. Okay. Since the current is flowing like this, this end to become positive and this end to become negative, and the current is flowing from P to N, that means it is forward bias. So the voltage will be 0.7 only, 0.7. So this voltage will be 0.7 volt, and this case actually, the old case actually, the voltage is Vz basically. So it will be 0.7. So I can, now I told you again, this is ground point. So ground point. Okay. Next, the diode is connected like this, and the current is flowing like this. So this is plus minus 0.7. So the output V out is directly connected to the positive, and the voltage is just 0.7. So the output will be 0.7 volt. That's it. Now again, that's it. Okay. So that is the beauty. Okay. So I hope that this is clear to you. Now I will give you to a problem to draw the output. That is, I have a Zener diode, okay, and this is my reference voltage, and I am applying V reference here, and this is my V in, and I am considering here a Zener diode in the feedback loop, and this is my V out. Whether this circuit is possible or not, is it possible to draw like this, to connect like this? If your answer is yes, if yes, draw the output. Okay, this is an homework for you. Okay, if you have any doubts, you can ask me. Okay, thank you.